Yes, sir. And are they all like SATCOM related?
The iDirect and the multiplexer can be connected to the SATCOM. You're going to see it in Block 9 in rooms 118 and 120. The TISR can be connected to the SATCOM. We've done it before. Oh, geez, probably about 6-7 years ago on nights. We set up a repeater system. We went from Foster's Manor to the Levittoll. The Levittoll had the repeater system and it relayed it to Jones Hall through this Jerk 239. The Jerk 239 pulled its cable into the satellite, shot it to the SAT-SIM, back down inside room 120, so 120 could actually communicate with Foster's Manor and back and forth. So it was relatively a pretty cool setup, just showing you how it can interface with the satellite system. That answer your question there, Airman Mills?
Yes, sir. Thank you.
Sure. So, Mills, you play games, as in online games?
Yes, sir.
What do you play?
Right now, I play Among Us and Brawlhalla.
Okay. Stevens, do you? And so what?
Sorry, what'd you say?
What kind of online games do you play?
Oh, I'm not much of a gamer.
Okay. Have you played any?
Like, what do you mean online games? Like Xbox?
Yeah, you could say that. It doesn't matter what platform, whether it's PC, Xbox, PlayStation, Switch.
Back in my day, I was on Optic Gaming for Modern Warfare 2, Call of Duty.
Okay. Juarez?
Yeah, I was a quick scoper.
Good. Juarez?
One of the best.
I mean,
American Sniper.
I just play like Halo and such. Really play a lot of games.
Marshman?
Like Warzone, Call of Duty.
Okay. Thomas?
Sir, I play all kinds of games.
Okay. Bell?
The closest thing would be mobile games.
When you say mobile game, what are you talking about?
Like cell phone.
Okay. I mean, there's a bunch of games on cell phones. What do you play?
Madden Mobile.
Okay. All right. That makes a little bit more sense. And Quinez is typing his little message in here. And there's a reason why. Okay. Warzone, Apex Legends. Okay. There's a reason why I'm asking all these questions about playing games is because everything that we deal with is a direct relationship to how we play games and what happens when we have a ping rate really high or a ping rate that's acceptable. So when you take a look at these things, we are going to look at timing. So you can see those two games I play a lot of. Actually, I play a lot of World of Tanks, and I'm very well aware of the ping rate. And there is nothing worse when you're in the middle of an online game with others. Ping rate goes to the roof, and you get blown up, or you go in the water, or whatever. It's a pain when that happens. So we're going to try to explain in this particular objective why that happens. We're going to look at identify basic facts about timing synchronization standards. You do have to score 70% on the test. The idea behind that test is you've got 40 questions, an hour and a half, and you got to answer at least 28 of them correctly in order to pass. Now, with the AFSC application, just remember, you're going to be dealing with this. You're going to be dealing with multiplexers, modems, you name it. It's out there. SATCOM systems, Tropo, HF, everything is a direct relationship to it in how we're able to get information from point A to point B. This is just another avenue of doing it. We're going to go through the purpose of timing, timing standards, timing sources, time coordination, distribution agencies, timing jitter, and network synchronization. First thing we're going to be looking at, though, is purpose of timing. What is the purpose of timing? Bottom line here is we use a lot of timing to get our information from point A to point B, and if it's out of time, it gets jumbled up and there is no rhyme or reason as to what the heck it is on the distant end. So if you don't have timing and everything is based off of time, you're going to have problems. Like I was talking about the ping rate. Ping rate is one of those things where it glitches on its timing, and now it's got to resync itself to get back in time. It's very important when you look at this accurate timing and synchronization in all the stages. One of the things that we go through, this is a diagram, the purpose of timing. And this just gives you an idea of what is out there, and it relies on the purpose of timing. You got, in our case, starting from the top to the bottom is a NIPRNet, local switchboard, which is phones, and a SIPRNet, all running into a multiplexer. Multiplexer is just like a regular hub, switch, whatever you want to call it, just a little bit more sophisticated in how it takes differences of what kind of signal formats you have and combines them into one and sends it out to the satellite and links it to the next stage up into the sky and then back down to a distant station. So a multiplexer is what we are going to be looking at over the course of the next day or so, and then we're going to lead into the modem. Now this particular multiplexer I've worked on, it's called an SCC 100. The 16-channel multiplexer. It can take everything from like a NIPRNet or SIPRNet and local switchboard, run it in there. These are different signal formats. The multiplexer knows how to take those different signal formats and combining into a single aggregate. You guys are going to have to understand what an aggregate is. Nothing more than ones and zeros being sent out. That's an aggregate. It's also called mission bit stream and a couple other names that we'll go over later on in the block. Now you'll notice with the NIPRNet, non-secure internet. Now the way this works is you've got a bunch of computers all running into the multiplexer. And that is based off of time because you can't have all the computers going at the same time. This multiplexer has the capability of being able to look at that and look at those users and be able to differentiate who gets what time period when. You also have single users. Now, when you look at this multiplexer, you will see single users and multiple users. Not to be confused with the channels that are on there. Multiplexer, in this case, this SCC 100 has 16 channels, but you can see we got a lot more users in those channels. So sometimes these channels have to be combined with others. And that's how we end up looking at the purpose of timing. With that timing, we're able to select each one of these channels and give them a piece of time to be able to send their information out. We'll get to the more complexity portions later on in the block here. So with anything, we always start with the simple stuff and work our way through. We got a parent time, mean time, atomic time, coordinated universal time, and of course, my favorite, hammer time. You know, dun, 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 dun. You can't touch this? No?
Can't do it, sir. Can't touch it.
Yeah,
Can't touch it.
Hey, lighten the mood, right? So the first thing is apparent solar time. This is the first part of it. Easiest way to describe this is a sundial. Wherever the sun is, that's what it's based off of. But it is the least accurate because with anything, you have the seasons. The Earth tilts, has an elliptical orbit, so forth and so on. So that's the reason why this one is the least accurate. Then we start looking at how do we make it more accurate. Well, here's the mean solar time. This is where we started getting mechanical devices that kept time. Now, you always have some type of purpose or some organization that is going to take that time and try to be able to disperse it around the world. Well, this is where that universal time came into play because, hey, they figured that, okay, the zero line, the prime meridian, which is runs right through Greenwich, England, that's where the prime meridian is, and that's where they say time starts for the world. Not as in you go way, way, way back and that's where time started to begin with. No, they're saying, hey, this prime meridian is where everything starts as far as developing a 24-hour period. Now, please understand, again, they still have variations. There's still a problem with mechanical devices. But the bottom line is you've got universal time is GMT, Greenwich Mean Time. That's what it means. Then we have atomic time. This is where things started getting a little bit more accurate. Why? It's obvious. Atomic time is very accurate as far as keeping time. In this case, we use the oscillation for keeping our time. And again, they still say the GMT is still the world standard. We have something called this International Atomic Time. Well, wait a minute. If you look at that acronym, that doesn't make any sense, does it? You guys don't see the acronym?
Is that wrong?
It's backwards.
Backwards.
It's backwards,
because
yeah.
it's French.
Guess what? That is not English, it's actually French.
Oh,
Ooh, Thomas.
I guessed it right, sir.
Okay, so, and we're going to get to the organization that keeps, you know, the standards of time and other things. That the International Atomic Time is the way we say it versus the way the French words are spelled out. Coordinated Universal Time, again, if you take a look at that acronym, it's not right, is it? It would have spelled CUT, not UTC. Well, Universal Time Coordinated, you'll see it when I pull the website up here. The GMT is no longer a world standard. This was back in 1972. Yeah, I was alive for that. So what they've done now is they've combined it and called it UTC. Every now and then you'll hear someone say GMT, Greenwich Mean Time. Same thing as Universal Time. UTC. The idea behind it is we're still keeping atomic clocks to make sure that we get the accuracy from it. This is a standard throughout the world. There are 24 different time zones. You'll notice that I have a website up there called timeanddate.com. Highly recommend it. It has a lot of information based off of time. It does have a lot of the backdrop of the sun, the eclipses, things like that, that makes that website really easy to go through, and you understand it too. It does show UTC and local time and time throughout the rest of the world. One of the things down at the bottom here you'll see that we have Keesler Air Force Base, and then we have a time zone Z, 0 Meridian, or Zulu. Remember now, if you go to a base that has a mission-driven statement where they're launching planes and things of that nature, you'll go into some places where they will have a local time and a Zulu time. All missions are based off of Zulu, and that's so our military can stay on time in our missions, such as if we needed to bomb something and everything has to be coordinated. Everybody's going to use the Zulu time. They're not going to use the local time. Local time. Go ahead.
Zulu is the same
I couldn't hear you. Zulu is the same what?
all over the world, right?
Zulu is referencing the UTC, so it's throughout the rest of the world. Everything is based off of UTC. So when we go to this website, you will see that where this arrow is UTC. So if I grab this arrow and I point to that this is UTC, that's where the prime meridian is. That's where the started time. You'll also see over here the international date line. And what they have figured out is, even though this is the start of all the time, excuse me, right here, they still have to have, you know, for example, if it's 12 o'clock here, what is it here? So it's actually the next day. So this is our 0 time reference for UTC, and then you can see that we got a -1 hour, 2 hour, 3 hour, 4 hour. Now this is also in cahoots with being able to figure out if you have local time or daylight savings time. There's very few countries that have the daylight savings time. I know England has something called summertime, and then there is the winter time, whereas we have Eastern Daylight Time. I know it's really strange in the way they classify it.
So why do we need local time? Why don't we just use UTC?
Because the sun is different.
That is correct. Okay, the sun right here is different than the sun right here. I'm kind of getting in the area where we're at. So if it's 12 o'clock noon here, that's 11, 10, 9, 8. So it's 7 o'clock here. What's the sun doing at 7 o'clock in the morning? Or actually,
It's rising up.
It's barely rising. So the sun here, even though it's noon here, the sun hasn't even made it up over here in some cases. That's the reason why we don't use UTC. We use it as the reference, but because of the sun's rotation, time changes. Has to change. Because I wouldn't want to put...
So local would be more accurate?
Yeah, local would be more accurate as far as what it is in that place. But that's the reason why we have, you know, -1 all the way through, as opposed to over here, it's plus when we cross that international date line. And in some instances, you can see where we actually have +14, +13, and so forth and so on. The idea behind this whole thing is to show you universal time. Now, there are some specifics to countries. For example, if you look at India, look how different that is as opposed to this area. I'm trying to remember where that looks more Russia than anything else. You also look at Australia. The diagonal lines are half hours. Now, I do want to point out China. Look how big China is. It covers almost 5 time zones. Them as a country have said, okay, I only want to be 1 time zone. That way their whole country can be all on the same time. You know, you look at us, we have Eastern, Central, Mountain, Pacific. I think this is called Alaskan. So it just goes to show you there's different time areas, but everything is referenced to UTC.
We're on Central, right?
That is correct. And with daylight
So is
savings
Zulu
time.
just the military's version of UTC?
That is correct.
Yeah.
Timing sources, not to be confused with timing standards. Standards is where everything is logged against versus what the sources are that gives those standards. We have a primary and a secondary. The big thing on the primary and the secondary, and let me just give you an idea how this is going to work. For example, I see 1236, and I tell you, okay, we're going to break at 1237, be back by 1240. And at that point, what you're going to do is either look at your watch, look at your computer, whatever. What just happened is I've used my computer as a primary source. You guys are using your secondary source. You're basing your time off of mine. Now, there's other things that go through this. For example, the UTC, that's what we base all of our time off of as far as Zulu. And there will be a lag in some cases from point A to point B. For example, if we're trying to find out what UTC is overseas, there's going to be milliseconds difference between overseas and here when we finally get it. So there's primary sources and secondary sources. It just depends on how you run them. Normally, with a primary source, you want to choose the most accurate and use a secondary source as the backup. Every now and then, your secondary source will be the primary source. Let me explain a little bit. You don't think we got atomic time because atomic time was there to begin with. No, we had to get it from somewhere, and the mechanical time is where it started from. So it went from mechanical to the atomic, and you can see that the mechanical started out as the primary source. Now, as it turned around, holy cow, bugs. As it started out with this mechanical, obviously by going to the atomic time, it became more accurate. Two different types of oscillators out there. We have the quartz and the atomic. Quartz is the least accurate. Definitely a lot better than the mechanical. When I say the mechanical is the watches back in the day, they actually had mechanical devices, gears in there in order for them to work, and you would wind them every day. With quartz, what you do is use a piezoelectric effect. Does anybody know anything about the piezoelectric effect? Horace?
Can't say I do, sir.
Do you know? How about you, Marshman? Any idea?
Can you repeat the question, sir?
Yes. What is the piezoelectric effect?
I have no clue.
I believe that's the effect that the quartz will vibrate at, which determines.
Which will determine what?
Will determine the frequency.
Yeah, you need to hold down on your.
I'm trying. So fidgety and McRidgety, but yeah, I think it determines the frequency that it outputs.
Okay, good. Okay, so what you're doing here with the piezoelectric effect is you're taking a power source, applying it to an item such as a stone. Quartz is one. I've heard of mica chips where they make that device vibrate and use that frequency to base the time off of. Good. Two factors that limits its accuracy. You got temperature and aging. Temperature can be controlled, aging cannot. Over the course of time, it will degrade to the point where it will not work anymore.
Sir, what's an example of where they would use a crystal? Don't they use it in like conductors?
Crystals? Normally they use them for a couple different things. I've seen them in radios for frequencies. I've seen them in filters. Filters are big with that, where they generate a particular frequency using an oscillator, and they'll combine it. That's an oscillator frequency is how they work as far as timing is concerned. When I say timing, frequency as in the selection of a radio's frequency. Sorry about that. But they base that and use something called a phase lock loop to keep it on time or frequency, and use that frequency to combine it with another one to get a particular frequency out. Now, if you guys were in block 2, block 2, they use those to get the, I think it's 140 meg down to where it gets to the operating frequency of, 1.8 to 60 megahertz. Well, that's how they use it. Kind of crazy, yes, but they do use that. That's how we're able to filter that out. We'll show you when we get into the TISR. All right, atomic oscillators, we have 2. They're called rubidium and cesium. You can see these 2 on the periodic table. That's where you've probably seen them before if you've taken biology or some higher science in high school. They are definitely more accurate than quartz. You can see that the rubidium is the least accurate. You can see how much the clock speed is versus the cesium. And the drift. You can see that the rubidium drifts 1 microsecond in 24 hours. This one is looking at 200 nanoseconds in a 24-hour period. So both of those are atomic oscillators, and I've worked with the rubidium, the cesium, and the rubidium. I've seen in both ground stations and GPS stations. Of course, cesium is the more accurate, so the older GPS satellites that are up in the air, the rubidium would be the ones that are in there. The newer ones have the cesium, and they have upgraded to another one that they're starting to put in place at UTC and a couple other different organizations that rely on time. We'll go to that in just a minute. Speaking of those agencies, we're going to be looking at time coordination between these agencies, and what they did is they decided that there was 86,400 seconds for separate events in each day. These agencies keep that time for that place in the world. So with these distribution agencies, what happens is one is the keeper of time. It is the standard of everybody's. Then we have the agencies that distribute it within the United States. Let's take each one of these, such as BIPM, USNO, and NIST, and look at them. So BIPM is International Bureaus of Weights and Measurements. That is the American way of saying BIPM. It is based in Paris, France, maintains UTC. The big thing is it is the basis for the world. They are the ones that calibrate all the equipment. Most of it's scientific, and I'll show you from the website here what I mean about this. If you go to this, and let me click on this and blow it up for you. You see the top left-hand side?
Yes, sir.
Okay, you can see why it's called BIPM, and we call it something different. On the meteorology area, which is off to the right-hand side, you will see all the areas where they keep the standards. You got acoustics, ultrasound, vibration, chemistry and biology, electricity and magnetism, ionization, radiation, length, mass-related quantities. If you go all the way down to the next to the last portion there, you will see time and frequency. What this organization does is it has a standard that is kept throughout the world. So if you had an instrument, a scientific instrument that you think is out of calibration, you would go and take it to them and they would calibrate it for you. Because that is the world standard. That's the reason why they are the ones that keep the time for UTC. So they are the keeper of the standards, so to speak. When we get to USNO, this is where the DoD keeps its time, mainly for our GPS and our Zulu time and so forth and so on. Now you'll notice that on this particular one, you can see that we have a phone number down there, 202-762-1401. And what you will get is when they finally pick up, now I'll be quite honest with you, there are times where it takes a couple times of calling in before it will pick up, but it is a time hack. What does it mean by time hack? Well, every 10 seconds, it will give you the Eastern Standard Time for the United States, and then 10 seconds later, it will give you UTC time. Again, we go to the USNO website. There is a place in there where you can toggle into. I'm not sure if you can see it totally, but I'll just give you an overview of it. Off to the right here, when I pulled this and did a snapshot, it says Friday 05 June 2020 21:39:36 UTC. There is a place in there where you can see real-time UTC, and it will give you the milliseconds in the delay getting it from France to the United States. You guys know how it gets there?
Is it by satellite?
Underwater cable.
Really?
Yep. If you were to go to the submarine cable map, you will find, and most of this now has been replaced by fiber optics. But back in the early, 20s and 30s, they realized that they couldn't, when the phones started coming out and people wanted to communicate with each other, they realized that by laying down a cable all the way to England was I think that was the first one in how they were able to contact overseas. So by laying these cables in, they figured out that there's ways to do it. They got technology is better, and I'm pretty sure now that most of the cable has been replaced with fiber optics. Off to the right-hand side, you just can't see it. I'd have to expand it out. It shows you every one of the cables, and there is a lot of them, in what they do and where they go. It is amazing with this website. Okay, so we have USNO. We have NIST. NIST is an agency that distributes its time through frequencies. Now, when you guys are in Block 4, did you guys play with the radios and listen to NIST?
I don't remember talking about NIST or listening to anything about.
Okay. What you will get is when you turn to one of the NIST frequencies, you will get a couple ding, 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 or clicks, click, 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 over the airways. That's when you can receive it. And then it will give you a UTC time every 30 seconds. The only time that it will come with something different is think it's on the hour and half hour if there is some major problems within the United States, such as fires or a hurricane or tornadoes. But this particular website, NIST, has a history to it. Started back in the 1940s. I think it's 1940 when it became into play because they realized that they needed some way to communicate the time here in the United States. WWV is the headquarters. That's their call sign. WWVH is Hawaii. WWVV is Boulder, Colorado. They all work off of, actually VH and Boulder, Colorado work off of 60K, yes, 60K hertz, 2.5, 5, 10, 15, and 20 megahertz. There is a history to it, too. Again,
Sure, I have a quick question.
Go ahead.
Do we need to remember those rates?
What do you mean?
Like how you said the 255 and all that.
No, that's on the website. What you should know is when we look at NIST, you know that it's a distribution agency for the civilian side. DOD is USNO. BIPM is the national, the world. Where do we get, so let me ask you, where does USNO get its timing from?
It gets it from the cabling. That comes from France, I believe.
Okay, and what's the organization?
The organization that it gets it from?
Mm-hmm.
BIPM.
Okay, so where does NIST get its information from?
The USNO.
Nope.
Does it get it straight from BIPM?
Yes. There are two
Gotcha.
direct sources that go straight to BIPM to get their information. So that's where they base their timing. Again, if you were to go to this website, I gave you the phone number there. This one's, I haven't had this one not pick up on me, but I've had some problems in trying to get the frequencies to come up. But I have had the luxury on 2 occasions where I got to hear Hawaii and Boulder, Colorado. How do you know which one's which? Well, because of history, Boulder, Colorado is a male voice. Hawaii is a female voice. Normally, if you hear both of them, you'll hear the Hawaii one go off first, and then Boulder, Colorado right behind it. It seems like it's an echo. NIST.gov is the website. This is what it looks like. Again, you can go on there. They've got a lot of history to it, publications. They even have videos on it, which is pretty interesting. Next up, timing jitter. But before then, we're going to take a 5-minute break after I ask you a couple questions here. So, Senior Airman Bell, what does the piezoelectric effect do for us?
Give me 1 second.
Looking it up, right? Thomas, can you help?
I'm trying to remember because I remember it was towards the very beginning of what you said back when you were talking about timing.
That is correct.
But yeah, I don't remember exactly.
Okay, Thomas, can you help him?
Yes, sir. Is that the moment at which the crystal will vibrate?
Okay.
The frequency.
Yeah, and there were 2 things that you had problems with, Marshman. What were they? With a quartz oscillator, what are the 2 problems?
Oh, I'm drawing a blank. Uh-oh.
Juarez?
Could I? Oh.
See if Juarez knows.
hopefully I'm right, but it's not accurate. And something about
Temperature usually.
temperature. Yeah.
There you go. Mill's sliding in for you there. Temperature
Sorry,
and aging. Okay, Thomas. So you wanted to ask this question or answer this question. Which one can be corrected?
That is temperature.
Okay, good. All right. So I have.
So
go ahead.
Quick, sorry. So with the piezoelectric effect. What is the best way to explain it? Is just crystals vibrating causing frequency, or would you explain
you
it
have to
differently?
apply power to it in order for it to vibrate on a frequency, and it uses that frequency to reference time. For example, if you were to make it vibrate at, let's say, 20 kHz, and you're trying to get 60 seconds out of it, so now you got to figure out a way in how to divide it to where it gets 60 seconds. And there's ways doing it on a quartz. Normally the old digital watches had these quartz in them, and they've made great strides nowadays in putting a quartz watch together where it's very accurate. But back in my day, a Timex quartz watch digital was like $5-10, and it lasted anywhere between a year or 2 years, unless you sweated a lot in it, and it would just literally not work afterwards. But that's what a piezoelectric effect is referenced to. Is normally it's vibrating that crystal or some type of device, such as a mica chip or some type of rock that can vibrate when you apply a voltage to it. Any other questions out there?
Sir, how much power you put to the crystal? Like, if you vary the power on it, will it still vibrate at the same frequency because of how it's cut?
It is very possible, but also you run the risk of over vibrating it. Kind of like when you crank the volume up in your car or your stereo system, there comes a point where you got that thing on 10 and it sounds like distortion. So that's basically what you're doing to it. You don't want to apply too much power, but you don't want to apply not enough power. You got to find the sweet spot in there. Normally,
and wind-up watches aren't quartz, right?
Well, if you can find an old wind-up watch, or if you can purchase one, they're unusual items.
But they aren't quartz, right?
No, they're mechanical. I have an old pocket watch. It's about 60, 70 years old, and it's all mechanical. There are some pocket watches that rely on the quartz in order to make the mechanical work. Any other questions out there? All right, so let's take a break. Take a 5-minute break, come back, finish this up, and get into the next set. All right? Be back at 5 after.